Hello everyone, and it's my great pleasure to welcome you all to this bi-weekly IFRR Colloquium. Today we are hosting a conversation on quadrupedal robots. So let me start sharing my slides here. There's multiple reasons why I want to talk about quadrupedal robots. First of all, because we have it on our background slides of the IFRR, but I think much more importantly, because it's arguably one of the most vibrant research fields that we have in mobile robotics today. It is my great pleasure to welcome 4 distinct panelists for today's session. All of them have a very long-lasting experience in the field. I will not spend a lot of time introducing them, as most of you already know them, or you can look up their CV on our IFRR homepage. The first speaker is Sanbei Kim, professor at MIT and father of the MIT cheetah robots. Second, we have Claudio Zemini from IIT in Italy, who works on the hydraulic quadruped HiQ. Third, we have Ben Zilling, who is the mobility and behavior group lead for Spot at Boston Dynamics. And fourth and last, Avik Te, he's co-founder and CTO of Quadruped Robotics, which is a spin-off of UPenn. And finally, myself, I'm Marco Hutter. I'm professor for robotics at ETH and one of the co-founders of Anybotics, and I'm working with the animal robots. I will moderate this session. Now, as you can see, this panel that we have today is a broad mix from experts that work in industry and experts that work in academia, all on similar types of robots and similar types of challenges. And this will be one of the important topics that we're discussing today. In addition, I'm very delighted to also welcome our front row guests. Also there's a lot of experience in quadrupedal robotics. First, we have Xingxing Wang, who's co-founder and CEO of Unitary Robotics. Then we have Peter Fankhauser, co-founder and CEO of Anybotics. And we have Professor Katie Bill from UC Santa Barbara. She was working on a lot of different quadrupeds like Little Dog or Robosimian. Then we have Sonia Roberts, a PhD student at UPenn. And finally, Professor Hemon Park. He's director of the Dynamic Robot Control and Design Lab at KAIST. This time, I think it's also a big thank you for the people from Asia and people from East Coast for joining so early and so late in the day. The panel today will be slightly different to what we have seen in earlier colloquia. We are planning to do 4 rounds of short presentations. First round will be on design and actuation of legged systems. We will then discuss the underlying planning and control algorithms and the trends that we see in that field. Then we give you a bit of an insight in where we see today's applications and where these applications will go in the near future. And finally, we have here a selection of people from academia and industry. And we also want to discuss with them a little bit what is the role of academia and industry and what are the open research questions that remain to be solved in the near future. We will do these presentations in the order how I introduced the panelists. So I ask all the panelists to stick to the time they have. And after every round of presentation, we have time for some questions by the front row. At the same time, I invite everyone who's in the call to post and upvote questions on Slido. So there's the link is here on the slides, and we also post the link in the chat. Now, before diving into the discussion, I want to spend a few minutes to get all non-leg robotics experts in the call a bit up to date. And I think without discrediting a lot of the fantastic research on quadrupedal system that was already done in the 60s or even earlier, it's probably fair to say that like the breakthrough and also the work that really heavily influenced most of the research that this panel here is working on happened at the Leg Lab with Raybert and a fantastic group of researchers, where they developed some of the first really dynamically balancing quadrupeds, which then later through Boston Dynamics led to Big Dog, which is probably one of the first publicly known quadruped who was really operational in the field in rough environments, and also probably one of the first robotic YouTube stars. Now, the reason we want to have this panel is that over the last decade, we literally saw an explosion in the number of quadrupeds. But not only their numbers increased a lot, also their skills and the range of applications. So please don't blame me for missing out robots in this illustration. It's not meant to be complete, but I think it gives you a little bit of an impression of where the community goes today. And this brings me to the first part of our presentation, the first round of presentation, and I ask the panel to give you some insights into different platforms they made and they're actually working with. This I hand over to Sandeep.
All right. Do you want me to share a slide and 3-minute presentation, I guess?
Please directly share your slides and it will kick me up.
All right. All right. Thank you so much. This is Sang-Bi Kim. I will give you a very brief introduction on my work on mostly actuation and then quadruped design. My career last 10, 12 years is mostly focusing on paradigm shift. Robotics history is primarily anchored on this manufacturing side. And as you already know, manufacturing task is actually very unique in a way that is position control, predetermined position control basically dynamic. So if you think about the environment, everything is grounded mostly, and everything is structured, everything is known position. Rarely you want the robot to interact with some dynamic forces or impact and high speed motion. So when it comes to any application outside the factory, you have to think about many different things. You have to think about robot actually has to move around. And that already give a huge challenge, because if it's rough terrain, you cannot use wheels, and then every step is going to be impact, and that's going to basically negate all the technology we developed the manufacturing robots. And you have to balance, because the robot might have to be upright, not necessarily flat on the ground, and you're going to have to deal with a lot of interaction, impact, and force control is more important. So I think I've been working on this paradigm shift in many aspects. Probably the most important, interesting thing is the actuation. So ever since at MIT, I've been working on how to characterize the actuator in a way that is more friendly for us to use in the dynamic environment and unknown environment and outside the factory. So the video you can see in the left is like we made in 2010, 2009, really focusing on maximizing force bandwidth and minimizing operation space mass matrix. So that's how we actually maximize the interaction force control bandwidth. At the same time, it can minimize impact force. So I'll quickly show you a series of robots we've been working on last sort of 6-7 years. So this is a Cheetah 2. This is probably the first robot we made it in balanced control working on 3D. This is actually developed by controller developed by Professor Park and the panelists, the front row. This is the first time we actually integrate the vision sensor to jump over obstacle autonomously. And as you can see here, the landing and then impact is actually most important thing, because in leg robot, inevitably, unless you're moving very, very slow, every step will cause a heavy impact. And this is not very unique for leg robot, actually. If you think about any manipulation, unless you're moving, dealing with a very small object, your hand actually collide with the object constantly. If you imagine you open the door, imagine you grab something, anything heavier than your hand, even a mug is actually heavier than your finger. Then your finger is constantly colliding. And then this is going to be critical for robot when you design a robot that actually operate the task almost as fast as human. This is a mini Cheetah. This is probably the greatest, smallest robot we ever built. And this is performing regulated model predictive control that developed by my PhD student. This is probably the best blind controller we ever had. We're still trying to integrate this with the vision sensor. But as you can see, the dynamic capability is exceptional because of our unique design, focusing on IMF, impact mitigation factor, which pretty much describe the characteristic of the high force bandwidth and minimum inertia. This is some preliminary work in our vision integration. Nowadays vision sensors and computers are developed progress so quickly, we have to keep on moving on to new hardware. We're learning a lot on vision, odometry, and planning. Thanks to our practical, like small cheetah, we actually built many of them. We're sponsored by Naver Labs. We built many of them. We were actually starting our loan program. So currently have a 6 institution actually have this mini cheetah, and then they are operating their research on mini cheetah. I hope that gives you some overview about my research, and then we can start discussion on maybe design and quadrupedal robot.
Okay, I'm next in the row. Can you hear me?
Yep.
Hi all, my name is Claudio Semini, and first of all, thanks a lot that you invited me for this prestigious panel here on quadruped robots. It's a pleasure and an honor to be there. So my lab has 14 years of experience in building quadruped robots, hydraulic quadruped robots. The lab is also writing the algorithms and the software to make them move. So this includes control, planning, and perception. And over the years, we have developed different platforms. There's the HiQ, most notably, HiQ Max, and then HiQ Real, the most recent platform. So just to give an order of magnitude, these robots are around 90, 80, 130 kilos. The last one has hydraulic power on board, so it's a bit heavier. And they're about 1 meter, 1.3 meter long. So they're slightly bigger robots than the other robots we're probably seeing today. So this is one of the very first trials of making HiQ walk. This performance is very, very poor. I've never put this video online, and you know why. It's really poor performance because we're using position controlled. These are valves that are proportional and have a big overlap, and were the wrong choice. So shortly after, we bought a series of these Formula 1 servo valves from Moog, and they changed everything because we were able to implement very high performance model-based torque control. And you can see in this 5 Hertz motion with the hip and knee joint, we can get beautiful performance in terms of joint position tracking and joint torque tracking. Now, if you have a good joint torque tracking, you can do nice things like impedance control. We've seen it before also from Sangba's slide. Here in this case, we're controlling stiffness and damping in real time. There's no other spring in the system. I'm playing here with the stiffness of the knee joints, and here Thiago is playing with the stiffness and damping of the leg, because we can map then this stiffness anywhere in the space. And this shows nicely already the advantages that we have from the hydraulics, so especially the impact resistance, but then also the very high speed and torque density, the power density, and some other advantages that we could talk about later on. Okay, I hope you can still hear me. I think my sorry guys, I'm not sure what happened.
Yes. Are you done, Claudio? Some more?
No, I'm not done. Sorry guys, sorry. I think I have a problem.
Sorry,
with the internet.
I jumped the gun there. I thought you'd finished. Okay, please go ahead.
Oh, sorry. I think it's my internet or my computer. If you can see this slide again, here is just a short overview of what the HiQ robot has been doing in terms of locomotion performance. We have a few videos here showing the. I don't think all of them play, but anyway, the top right you see a balancing of the disturbance. Here in the bottom left, you see climbing, and here you can see the robot navigating over rough terrain where rocks are not fixed. The second generation of HiQ is HiQ Max. We see here HiQ performing some trotting, but then also self-righting. This is one of the skills that this robot has. And what was mainly missing here was power autonomy. And so around this time in 2015-16, we teamed up with Moog because they had a beautiful 3D printed titanium hydraulic actuation that we could use for our 3rd generation robot. And this is the high-key reel robot that we brought to the airport of Genoa to pull a 3.3 ton airplane, a small passenger airplane, to demonstrate the capabilities and force of the machine. What about the problems? I tried to close a few applications on the laptop for the next round.
Okay, so then I think Ben can take over.
All right, good morning. And I did take the liberty of adding a blue spot down, hanging out with his friend in the bottom left corner there. So this is a limited lineup of some of the quadrupeds that we've built at Boston Dynamics, and basically Boston Dynamics was a spin-off from the Leg Lab. We've been, Boston Dynamics has been doing quadrupeds as Boston Dynamics for almost 20 years now. Starting off with in a variety. So starting off with LS3, formerly known as Alpha Dog, which is a large hydraulic machine, about 1,200 pounds, fully loaded. Then you go to something like Wildcat, which was our fast runner, and it got up to about 19 miles per hour. Again, also hydraulic machine. And Big Dog, yeah, we already talked about this robot specifically. Here he is on a beach. Big Dog was, the first successful quadruped. This is actually, again, hydraulic robot itself. So you notice a theme here. And then, okay, this is Spot Classics. So this is the previous version. This is also a hydraulic machine. So you hear me saying hydraulic a lot. So we actually have a large experience. And then, okay, there was Little Dog as well. Not quite the same as this was, primarily research, didn't actually go outside. And then Spot Mini, and here I am doing, it had an arm, and we were doing some testing of manipulation efforts. And anyone who's done robotics and interaction with robotics, things don't go according to plan all the time. And delivering the beverage failed a little bit in that effort. So going through the lineup again, and yes, okay. So there was a couple of characters that missed this whole layout. Yes, so starting with LS3, so 570 kilograms, fully loaded, has an internal combustion engine. Big Dog, almost 200 kilograms, internal combustion engine. Wildcat, almost 100 kilograms, high speed. Spot Classic, actually, so we didn't have an internal combustion engine, but was still hydraulically powered. And then you get to Spot. And Spot was a little bit of a departure for us because, okay, now it is electrically actuated and battery powered, and it's only about 30 kilograms. So a little bit of thoughts on actuation in general. So we have a large experience with hydraulic machines. The reason being for hydraulic machines is you get great power to weight ratio. Unfortunately, as you have to send the fluid across all the joints, there's some fluid routing complexities. So you're going to have hoses, or you need to have internal routing throughout the structural material of the robot itself to send fluid. There's some safety concerns. Actually, that was one of the chief primary drivers for Spot when we went from Spot Classic, which was the 160-pound robot, to the version of Spot that we have now, which is about 70 pounds, with safety concerns. That having people around with high pressure oil and high temperature oil wasn't the best idea. With hydraulics, you end up with a lot of power loss for movement. That basically anytime the joint is moving, you're spinning off 3,000 psi oil into return pressure, which is about 30-40 psi. There are some rotary actuators. However, most of the time in implementations, we use the linear actuator with some sort of linkage. It would be a 4-bar or a cam. Electric actuation, torque control is much easier. You don't run into the issues that Claudio mentioned a little bit about, okay, what kind of valve do you have? What is the what does the lapping on the spool look like? Is there a null on the spool? Electric actuation, there's some scaling issues. You notice that it's not a accident that Spot and LS3 are order of magnitude different in size, and only one of those is electric actuated. And one of the big things here with electric actuators, there's no oil leaks. Hydraulic robots are getting better for regards to how much oil they leak, but it used to be the time that our lab floor was, cleaning up oil spills was a common occurrence. So, all I have on this one. So, Vivek, you want to take it over?
Yep. Yeah, thanks, Ben. Yeah, my name is Avik Day. I'm a co-founder and CTO of Quadruped Robotics. Very, very happy to be here in this panel. Yeah, so the first topic about hardware. So we make actually two kinds of robots, and the rough size and scale, you can see like the bigger robot is called the Vision 60, and it's capable of stair climbing. We kind of sized it for that purpose. And there's a smaller robot called Spirit 40. And the numbers roughly correspond to, but not exactly correspond to the hip-to-hip distance. So there's that. So that's about the size and scale. So our design priorities were definitely to keep the design cost effective, go for efficiency in terms of power, mechanical efficiency. We use common hardware components as much as possible. These are all electrically actuated, no series elastic anything, and kind of common drivetrain so that it's cost effective to manufacture. We chose to put a lot of the complexity in software, not hardware, so remove external sensors as much as possible at the toes or at the joints. And tried to make these robots weatherproof, the larger one at least. The limitations of the design is, we didn't really design them to be payload mules. So as you can imagine, this is not fixed. So like, in different conditions, the payload amount can vary, but for the Vision 60, you advertise about 20 pounds. So that's not something we were striving for. So the thing we've spent a lot of time on is optimizing the designs for the fundamental constraints of force and power. So the reasoning is that, when we talk about autonomy, which we probably are going to do at some point today, power autonomy is obviously a fundamental component of that. And we wanted to maximize the range of the robot before it needs to be recharged. So here you can see a plot that I pulled out of one of Sangwei's quite influential papers that we read on this topic. So the Vision, the total cost of transport, including everything, is quite good depending on the terrain that it's operating on for its body mass. And here you can see a rough breakdown, and as you can imagine, most of the power is consumed by the motors, but we also actually spend a lot of time on making sure the power consumption computationally is also not a large component of its total power consumption. So the way we approach some of this problem in a pretty kind of size and robot scalable way, so applies to the Spirit and the Vision, is that we build models to kind of simulate the power consumption and optimize the drivetrain components. So we use, let's say some combination of simple models and past data to project what the robot's gait kinematics will be for a variety of tasks, and combining with some expected dynamic parameters of the robot, we can use the forward dynamics to get the kind of the gait dynamics, and with the motor parameters together, we can kind of project what the torque consumption or the torque production and the velocity of the joints will be, and get some idea of the power consumption. But as you can imagine, this is a very high dimensional kind of design optimization problem with all sorts of factors such as impact mitigation, which Sangwei mentioned, electrical constraints, and really we've put a lot of time into this kind of framework to allow us to get high range on our robots. So that's kind of where the designs are coming from. So that's what I have here. So I'll stop and put it back to Marco, I guess.
Thanks a lot, Avik. So with this, we're done with the first round, and I would like to open up for the first set of questions for the front row. So who wants to start with that?
So I have a question. Some of you touched on this a little bit, but it's not clear to me how you chose which actuation system to go with. It seems like actuation is going to affect what the applications are going to be. So are you starting from that perspective? Are you starting from a cost efficiency perspective, an ease of manufacturing perspective, power to weight ratio? What are you guys thinking about when you're choosing your actuation scheme?
I can start. I mean, we've been focusing on highly dynamic, like, there's a lot of criticism about the terminology, but, fast and very powerful motion. So it will handle a lot of impact. And if your actuator cannot absorb those power, not let alone generate the power. You can't really do experiment, and it's not going to be useful in real life either. So we've been focusing on this. Basically, high force bandwidth is the right term. That basically bring up impact mitigation factor and low inertia, the low impact force. All that actually good characteristic of a proprioceptive actuation is summarized by high force bandwidth, because if you can change the force quickly, which means you can observe force very well. So you can design many different way, but we happen to choose high torque density motor with the low gear ratio, happen to be planetary because it has a more load taking capability. You can design different way, so you can't really talk about like which transmission is better or not. I think that's where the IMF really comes. Impact mitigation factor summarize all these. So it doesn't matter what kind of motor. Actually, you can use a skinny motor with a different transmission. As long as your IMF is high enough, you can actually handle that. So that's how we've been choosing our actuation scheme. Of course, if you try to do high payload, relatively slow motion, you gotta change the design and do something else. So that depends on what you want to do.
Thanks a lot. And due to time, we move on here. So let me again share my screen. So I think Sonia raised one important point, and that's something in my eyes that we observe in all these developments. If you look at these machines, they're all different in their size and detailed design, but they also share a lot of common grounds. Besides having like 4 legs and typically 3 actuated degrees of freedom and point feet, the similarity is also on the actuation side. Whether it's electrically or hydraulically actuated doesn't really matter too much, but I think we can really summarize that the community has converted towards robots that are torque or at least impedance controllable, with actuators that have that are dynamic and impact robust. And hence these robots, they can all be modeled as kind of a multi-articulated torque controllable system, which makes it also easier to share control paradigms among them. So to control these robots, what we are typically looking at is, in a very classical setup, is that we have some sort of a high-level intelligence for the whole system, which tells us where to move. And we have a planner that aims at figuring out like how to move, where to step, typically by looking ahead for a short planning horizon and a short distance into the future. And very often here we're using like simplified models, so not the full multi-body dynamics, but rather simplified templates that describe the whole behavior. Now we track this behavior such that the motion is executed with all the constraints that has to be satisfied, some reactive behavior is included. And then only at the very lowest level, we have the machine relevant, machine specific joint level controller. And of course, there's a lot of feedback involved. I don't want to tackle this too much, but you need to know how the machine is moving, how the environment looks like in order to do this planning. Now, over the last couple of years, there's also an alternative approach which has picked up quite a bit. We have seen tremendous progress in reinforcement learning for locomotion, planning, and control. So what happens here is that we are generating massive training data using simulators in order to train neural network-based control policies. And like iteration by iteration, you can have control policies that are getting better and better. And these controllers are really trained to cope with disturbances. They're also trained to handle complex terrain. So the better the robots get, the more tricky you make the environment in order to improve their performance. Now, obviously, what you're simulating is not exactly what you see in reality. There's a reality gap, and recently there has been methods coming more and more which are shown how we can possibly like close these reality gaps that we have between simulation and the real system by, on one side, stochastically varying the simulation and make it just more robust, and on the other side also by integrating models that are generated from real-world data. And in the experience that I have with our robots, this has led to behaviors that we were not be able to generate before. So like extremely robust behaviors, for example, after a fall, that the robot can get up again, so it can put it in arbitrary configuration and will find a way to recover from that and continue to operate. And this shows a little bit of where these robots can possibly go in the future. So not only being able to move around, but really use like full body contacts in order to locomote forward, and also to deal with like some of the most complex terrains, like terrain that is sliding and slipping, like loose grounds. If you go through a riverbed where you have like wet contact conditions, where you have slippery environments, and so on and so forth. So these are all elements which have or are extremely hard to somehow model, to simulate, or also to bring back into some of your model-based controllers. With this, I would like to go in the second round with this small introduction to the next set of presentations by the community here, and discussing a little bit in how they're controlling their robots, and maybe give us a bit of an insight into these model and learning-based locomotion controllers, which you already see that there's plenty of questions in Slido about that. So again, let's start the round. Sangbe, if you can take over.
Yeah, I will just talk in the control side. We primarily focusing on the MPC, model predictive control. As you know, the quadrupedal robot, like its design is converging to this 3-degree freedom per leg, like 18-degree freedom. It's already pretty complex system, let alone, we have to keep in mind our animal counterpart has about 700 muscle. So, we're trying our best to minimize our number of degree freedom, yet it's still too complex to model the entire, include the entire mass matrix and then every inertia to use to the simulate forward to get the simulate predictive control. So we primarily took the initial approach from Boston Dynamics. Basically, they been showing this for many years, using rigid body, like the one rigid body, the most important inertia. So we took the body, one rigid body model, and that's how I actually also designed the robot. Like most significant portion of the masses are concentrated in the body. And then we assume that each shoulder acts as kind of some sort of thruster based on what actuator can handle. And of course, non-linear constraint come from the friction cones and so on. And then model predictive control basically produced this very crude approximation of force I need to generate given situation, looking ahead about a step forward. So there's no model accuracy involved, and the question is it good enough to give us the right direction of force? Our initial model predictive control have run only like 40 hertz, which means you only have a 3-step chance to change the force during the contact time, because our contact time is very small. So if you compare with our MPC result to real result, they're not really matching very well. But we believe that the robustness is not coming from accuracy. Robustness is coming from the fast calculation and right execution, right approximation of the model. So that's pretty much what I've been working on. Of course, the whole body dynamics come in here and to clean up all this accuracy issue to make it better. But whole body dynamics only running at real time, so it doesn't have any forward looking capability. It's still interesting to see what we can add using like a data-driven machine learning type of approach, where modeling is very nasty, like the Marco introduced like a multi-contact situation, or like complex like leg swing planning on very complex terrain. We see there's a definitely benefit on including the data-driven approach, but we haven't done too much on that section. So we're pretty much focusing on model-based approach at this point. Yeah.
Okay, I hope it works better now. Right. So in this part of the round, in the second round, I will bring 3 examples of how we use machine learning and model-based controllers in our locomotion framework. First example is about machine learning. So here we use a stereotypic gate, a blind gate, that then has nominal footholds where the foot swings next. In this particular case here, it's shown with a red dot. But we have trained a neural network to analyze these height maps around the nominal foothold to give certain corrections if they're needed. So in this case, if there's a gap and potential shinkulation or getting stuck is a risk, then the neural network spits out a better solution in a better foothold. And this green foothold. This works very well. I hope you can see this simulation here. We can see how the robot overcomes these gaps. Sometimes it decides to swing over two gaps all at once, and other times it needs to step twice on the same step to not step into the gaps. We also brought this onto the robot, of course. This is a 0.5 meter per second trot on a very similar terrain with gaps. You see the robot is not stepping any time into these gaps. And also this works very well when we are disturbing the robot. The robot is told to step in place, but then Victor, with the help of Octavio, are pulling the robot here towards these gaps. And you can see the robot can do these micro corrections in few milliseconds and not step into the gap. And we're using here also the speed of the robot, of course, to adjust while swinging where the nominal foothold is going to be. So in terms of model-based controllers, we heard it quickly, the whole body controllers. I think most of us use these full 18 degree of freedom rigid body dynamics models, which include all the degrees of freedom of the joints, but also the 6 DOF of the floating base. In this particular example of a few years ago, we're optimizing the ground reaction forces here to stay in the friction cone. This is Michele Focchi who made this chimney climbing, inspired by climbing. But then Chamel, a few years later, improved this in a sense that we can cope here with soft terrain. So here the robot is actually first estimating the compliance of the terrain foot by foot, and then making the adaptations in the control accordingly. Something more recent, where it's also more model-based. Here we're using a simplified model, the central dynamics, to improve a very well-known concept of the support region. You see here in the image in the bottom, and the support region is the support polygon that is spanned open together with the feet. If we improve this in a way that we can include also the torque limitations of the machine, so all the joint torques get fed into this feasible region that is a very simple representation of what is the robot still capable to do. In this video here, we're adding more and more force vertically on the robot to like simulate an additional payload up to 600 Newton, 60 kilos, and you see the feasible region is shrinking accordingly to getting closer to the joint limits. More recently, we've extended this also with kinematic limits. So here, these are the joint limits. If the knee here is getting stretched almost completely, you see the improved feasible region is actually shrinking accordingly. And this is very powerful to think ahead and do simplified planning for the locomotion. So this is what I have for round 2.
Thanks, Laura. Ben, you're mute.
Sorry. The layered approach, Marco, that you showed I think it's going to be pretty common across a lot of robots that we see fielded. So, at the top level, we have navigation autonomy. The video on the bottom left is showing the robot doing, the navigation system is doing building scale, room scale, localization, and autonomy. So giving the robot a position in XY theta. In this case, as we're going up the stairs. After that, we have what we refer to as a sequential composition. So that's the picture of the funnels sort of on the right side. And really what that means is that you're in some domain, in some state space, you're going to find a region that you think that this particular primitive is admissible, that it can run. And the example that I'm going to give there is if the robot is standing, you're going to look at something like a support polygon and where your capture point is inside that support polygon. And then if it goes outside of that region, okay, well then I need to transition to something that's going to take a step. This is how you decide that I've gotten kicked, I need to move somewhere. After that level, once you've decided what primitive, what controller you're going to run, we have foot placement and local obstacle avoidance. That's the picture that's sort of going on in the green and red, that we're avoiding that, that red circle. And at the very low level, you have force control. Obviously, you need high bandwidth force control and tight position control when you finally get to a swing. So spot mobility, yes, we use a variety of model-based controls. We actually don't do a whole lot of learned controllers right at the moment. They're primarily using simplified models. So most of our gate selection and foothold selection is using a linear inverted pendulum. However, we do use what we refer to as the single potato, the full, one DOF, base link, and we do, full rigid body dynamics at the, not quite the lowest level, one step above that. The linear inverted pendulum, it's fast to compute. There's some easy analytic solutions for things like, our steady state walking and trotting, where the body, its orientation is not moving around a whole lot. We can sort of neglect the orientation effects. It's actually, we found it to be remarkably robust. Things like center mass height, robot payload. A lot of our recent development has really been targeted towards constrained environments. So stairs, this is all sort of, some of it's actually perception informed. Stairs, slippery terrain, foothold and body constraints when you get around, moving past, obstacles, not hitting them, walking through tight spaces, and the reliability for mode installations is a primary concern for us as well. Just getting back to where can we use machine learning? We expect that Spot's core balance algorithms remain fundamentally model-based. It is working well for us. There is easy extensions towards coupled mobile manipulation once you do model-based control. If you have a model for what manipulation was doing as well, Spot, you can buy it with an ARM or not. I will say that I think the last 2 years have proven that these sort of model-based skeptics of casting an eye towards the learning approaches. I think we've proven that, hey, you can actually do some really great stuff, and I think there's some really good work that's going on. We are actually doing some active development in learning, some opportunities. Yes, learning cost functions for foothold selection, domains, as I showed for that controller selection, in sequential composition, scene understanding, knowing which part of the world we can step on, which parts we can't, which are things you don't want to walk into and hit. Obstacle detection, anomaly detection. Can we detect errors with the robot? Can we detect errors in the world? If the robot is doing remote site inspection, can it detect something's wrong in the site today versus yesterday? Detecting movers, things in the world. Obviously, robots, we want to be concerned about them interacting with people and hitting people as well. Terrain segmentation, understanding, okay, this part of the ground is gravel, this part of the world is slippery, that sort of thing. And I presented like the mirror puddle problem. Spot has 5 stereo cameras all around the robot. If you're on a construction site and you have standing water, this is going to be reflective. This looks like a alternate flipped world that is, in the ceiling, and the robot thinks, okay, now there's a hole in the ground that it's going to fall into. Can learning help us solve that problem and identify puddles that you're not going to fall through the floor? And that's all I have for this one.
Yeah, great. So the motivating question I thought was quite interesting. I mean, we get I get asked this quite a bit. So I try to not think about it as a versus kind of thing where we're preferring one approach versus the other. So if you think about like the models that we need to use, so we talked about the potato. I just took a picture out of Sangwei student's thesis here. Or maybe we need to think about where the toes are going. Like this is a picture of a staircase with some overlays, and obviously there are a lot of obstacles here that the robot has to avoid. Or you think about really unstructured terrain where it's just very hard to pick where the body is going to go and dynamically stabilize. So I see as this as kind of an increasing complexity hierarchy of models, and the approaches that we take to solve the problem should probably be kind of connected to the type of model that needs to be used. So for instance, if we only need to stabilize the torso, maybe models like the LIP, maybe even reactive strategies are able to give us some helpful answers. But maybe if we need to think about a lot more complexity, like the stairs or other geometric constraints, that we can't use that kind of simplified controller. So the thing that we've found is, and this is not something that has been completely proven, but the generalizability of the controller and the assumptions that it makes about the environment roughly seem to follow this trend. So I'd love to be proven wrong about this, and I think there's ongoing research in this area, but that sort of limits how generalizably we can use certain controllers if they're developed with these techniques. And on the other hand, you have, if you think about the total computational power that's being dissipated by the robot. So roughly the complexity of running a single step of the controller times the frequency at which it's running will give you how much computational power is required. And certainly you don't want to be down here where just for solving a simple problem of keeping the torso upright, you don't want to be spending a ton of computational power. That wouldn't make sense. So we try to balance these things, and we're obviously also continuously iterating. So for the torso and toes problem, we use an approach where we kind of model predictive kind of approach, as we've discussed already in this panel, and with the hierarchical kind of model structure. But for some other situations, we can use purely reactive controllers, so just for kind of running and stabilizing on ice. And the reason I showed the ice video here, and also actually we've done some stair climbing with our robot completely blind. So the robot doesn't have any idea of where the obstacles are. All of the reactions that are very necessary to keep the robot from falling over instantly are all reactive, and just try to be these kind of preflexes, as they've been called in the literature. The reason I showed the ice video here is because, as you can imagine, like making more assumptions about the environment is how the ice environment, the robot would fail in that kind of environment. So we try to obviously keep our controllers not making too many assumptions when they don't need to. Actually, pretty similar to the mirror puddle problem that Ben mentioned. So if the robot's blind, obviously it doesn't care about the puddle. So yeah, so and there was a leading question about what's missing. So the question marks that I put on the right, at least to me, I think there's sort of some mysteries over there about how to use the methods that can deal with more complicated obstacles, and also decide how the robot should coordinate its legs and not just assume fixed gaits and things like that. So animals can obviously do this quite well. So this little goat here is not following any fixed gait coordination pattern, but able to kind of generally have a general kind of dynamic stability, which I think is a great kind of motivating thing to think about for the future. So yeah, that's what I have for this.
Thanks, Avi. So with this, we close the second round, and we have time for a few questions. I can maybe propose one from the Slido. So the question there was, what is a moderate form of compromise between machine learning approaches on one side and modern control theory for quadruped robotics? And I think like some of the answer we have already heard here. So if we keep a lot of the structure that we have from the classical known model-based controllers and replace part of that using machine learning. I think Claudio showed this very nicely. We've seen it also in the talk of Ben, that like some of the cost functions and things which are very hard to like handcraft, these things are done by machine learning, but there's maybe other things that people want to add here to this answer.
I'd like to add a cost function aspect. So we did some sort of like a very like human in the loop kind of learning kind of approach we use in the regulated model predictive control. Finding cost function, I mean, in the machine learning community, typically they set the cost function very simple, like go as far as possible, like, and you find like there are a lot of unpractical thing, and we as a community, most of the model-based controller, even model-based controller, the cost function is something very difficult to find. I mean, we've been all doing hand-tuned, but even using machine learning, we need to have some sort of a quantitative target to modify these parameters. And human has a great ability to determine this is better running or not. My student actually took it apart in the data and then selectively choose like this I want to be 0, this I want to be free, And then he did that kind of like a data-driven feedback to modify our cost function. But if you purely rely on the machine learning without having this kind of human intervention, we need to really think about how do we quantify this like a human-centric desire, run well without falling. This is constantly popping up in our lab discussion. This is a very abstract goal. If you cannot quantify properly, machine learning also will suffer in the process of the tuning these parameters. So I think the cost function is the key to improve our technology, either machine learning or model-based control.
Thanks. Any other questions that we want to answer to this topic, or should we move on?
I have a kind of follow-up on that. So we're talking about machine learning versus model-based control, and in both cases, it's very important that you have a good simulation, depending on how complicated your model is. Marco had touched on the idea of increasing robustness by having variability in your simulation, but sometimes you want to have agility by just having a more accurate simulation. So like for Marco, there's a difference between learning the internal dynamics of a system, maybe the actuator dynamics, versus learning the contact dynamics. Contact dynamics is really hard to model. I know Boston Dynamics uses, very good simulators to be able to get where they're going. What comments do people have on the importance of simulation, the making your own simulator that works well, and the failings of simulators today? And can we use machine learning to improve our simulations, to use sensory data? Ben had talked about using visual data to have a better situational awareness for Spot. Can we use our sensor data to have a better simulator that we can run offline to get control online for a robot? There's a lot in there. That's like a lot of questions. So pick and choose what you wish to respond to there if anyone has comments.
I guess I can give a short answer. I certainly wouldn't want to pretend to be able to speak to the ability to learn about the dynamics. Honestly, our approach has been often that, the simulation is only, kind of part of the way for debugging, but the ability to have, the robots not break, and, robots like our Spirit or Sangway's Mini Cheetah that can be, quickly used to test stuff out on the real world with all of its messiness has been quite valuable for us. We don't spend a lot of time trying to develop our simulation tools because it's not something we're that good at or don't have the resources for, but it does speak to the need to perhaps have robots that are robust and can be quickly manufactured and things like that.
Maybe to give an answer from my side. So we did a lot of investment on that end, and I think there is hope also that we can bridge some of these reality gaps, things that we cannot really model from first principles, that we use data and capture that and bring that back into the simulator in order to have simulations which are more close to reality. And I think in particular also for like this direct zero-shot transferring from what you train in simulation to bring that to real world application, I think this is very, very critical. So a lot of the stuff that we did initially with like off-the-shelf, not very precise simulations did not work out in that context.
Yeah, I just wanted to note one more comment there about, basically closing the loop a little bit with the simulation. Obviously, simulation is hugely important for us. Just for every version of walking that we've had, it existed in a simulator at first, but just for production things that aren't super exciting from a research perspective about unit testing to make sure that somebody's last code change doesn't make the robot fall down. So any code change needs to go through a series of hundreds of tests to make sure mobility is not affected. In regards to closing the loop, we have gone back a little bit for things like noise models for a gyro and force control bandwidth, because obviously a simulator you can end up with infinite bandwidth there. So we have done that a little bit. We have not done anything with learning specifically. Our drive towards simulator is really to get a combined perception camera model plus control model plus physics that are good enough. And good enough is actually pretty important because we know that the robot is not going to act like the model. So if the simulator also doesn't act like your simulated model, your simplified model, that's okay because it actually introduces an error there.
Thanks. Yeah, and I think I can remember Al Rizzi from Boston Dynamics talking about some of the initial Big Dog video with slipping on ice, that the robot doesn't know that there's ice, it just knows it needs to find the right foothold to be able to arrest angular momentum, be able to stabilize itself. And maybe it's not a big deal if you had a better model for the ice, maybe it's just important to know where I want to put my foot. What do you think the diminishing returns are on having better models specifically of the contact dynamics and specifically for a quadruped as opposed to a biped? I'm sorry, I already asked a question before, but just one last little thing. Because a quadruped is not as hard to balance, quite simply, as a biped. So maybe it's, yeah.
Yeah, I mean, the partially answering the question, I think when you try to make a contact, especially contact model closer to reality, and then everybody will have different opinion. In my opinion, it's never going to be accurate. In some metric will be better, some metric will be worse. And if you do some like machine learning type of approach and blindly just overfitting those wrong side, it's going to be problematic. So that's where diminishing returns come from, I think. And Ben mentioned this too, and then we follow this philosophy for a long time. If your controller is sensitive to those little minor detail in the model difference, it's not going to handle real world because you're going to see the real new type of grain somewhere. If you step on cat litter, if you don't model cat litter, it's going to fall. So your robot controller should have a cascading structure that has a robust enough, like a plan B, plan C, plan E, plan Z, without pure rely on this model accuracy. That's my opinion. In terms of the bipedal and quadruped, I don't have much bipedal experience, but we've been modeling a bipedal recently, and I think contact modeling is a lot more sensitive, especially if you use the ankle. The most of us using point feet for quadruped for region, even though animal, heavily utilize their ankles, and that's how they can stretch your leg and they have a wide range of having an ankle or not is hugely different. Somebody can add more, but the bipedal, I think the model accuracy seems to be more sensitive in terms of the control balance. So I agree with you. Quadruped is a lot easier because of larger support polygon.
Maybe just a few final remarks about the modeling. We're using, for our simulators, we're using standard tools with Gazebo. We have done some actuator modeling so that we can get the limitations of the hydraulics. They're usually almost negligible because they're super fast, but that can get us a bit closer to reality. And maybe another comment to something that Sangwei said before about the reliability and having a plan A, plan B, plan C. That's also our philosophy in having different layers in the controllers in which the low levels are reactive modules that run all the time with the step reflexes or then other balancing behaviors. And then if you get a little bit of visual information that is more reliable, then you can use that to do this very fast visual corrections. And if then you know that you have an accurate map, you can try to use that for more accurate planning.
Good, thanks a lot. We have to stop here and continue, otherwise we run over time. So let's go back to the next round. So I want to set here the stage very, very briefly. So I think what we have seen with like these amazing designs and amazing controllers that this is one of the reasons why we have probably this big of a rise in quadrupeds. We see probably exponential growth in the number of robots, number of publications, citations. The same happens also in the companies. So companies are popping out here and there, commercializing quadrupedal system. There's a clear trend going like from pure foundational research to commercial applications. Today, we're talking about several hundreds of quadrupeds that are out there, that are sold, that are used on a daily basis. And I think for us researchers, this sounds like quite a bit. We have to put this a little bit into perspective to like other mobile systems like HEVs, where we are 2 or 3 orders of magnitude higher than on the quadrupedal side. But nonetheless, I think like quadrupedal robots are a big breakthrough in mobile robotics, in particular in mobile robotics for unstructured environments, and like the door opener for many, many new applications. I'm showing here just like 2 videos and a couple of images of things you're doing with the animal robot, ranging from like deep underground missions to offshore sites far out in the oceans. And like most of the time today, the commercial applications deal with inspection, with monitoring, with mapping, where these robots go around to perceive the environment, they collect data, they feed this back to the operators of the ERP system of the sites in order to make these sites running autonomously. Now, with this quick introduction, I would open up to the third round of discussion here, talking about the different application domains that we are looking at today, but also maybe opening up for tomorrow. Sunday, you can start.
I lost my mouse. I'll be brief because I actually don't have much experience in real life application, but I will just share what I've been thinking. When I first started this quadrupedal project, like I thought if you make robot robust enough or fast enough, probably application will be unlimited. And then gradually realize moving around itself is not going to provide enough service. And as you can see, today most applications are inspection and gathering data, which is valuable, but true value probably will come when this mobile robot can actually provide some physical service using hand. There's so many arguments about like, if you're gathering data, probably like a drone can do it. There's other way to do it, like, surveillance, the 200 CCTV will, prevail, mobile robot and so on. So I think eventually we need to really integrate our arms. I don't know what the arm will do, but probably something to do with the arm. And that will actually open up another huge application area. And we'll see. There are, many, anybody who thought about manipulation is a whole another world, and the dimension just exploded compared to like locomotion. So I think that's going to be exciting future, but it's hard to predict in the future at this point.
Thanks a lot. Claudio.
Okay. I hope this is sharing. Okay. So here are my thoughts about applications. We're always thinking about applications because we're interested in pushing our things towards application and do something that is obviously useful. So the things we have been talking about for very many years now are the following applications: disaster response, precision agriculture, space, inspection, maintenance. And I'm really happy to see how the quadruped robots of the companies present today have done huge progress in terms of inspection, and then also gradually going towards maintenance and using arms, as we've recently seen in the spot video a few days ago. But we've been working on slightly different applications from our lab point of view, and I'm going to show you what we're doing in terms of disaster response, precision agriculture, and later on also space. First of all, disaster response, the teleoperation. This is a project that we've been working on for the last 3 years. This is financed by INAIL, which is the Italian national insurance against accidents at work. They're interested in protecting firemen from getting hurt during the work, and we were proposing here a combination of technologies that we have at IIT. This is a collaboration together with the team of Darwin Caldwell and Nikos Stagarakis. So our existing technologies in augmented and virtual realities here illustrated with the visor, and the hydraulic quadruped, electric arm of Nikos's team, and sophisticated hand-arm exoskeletons for haptic feedback resulted in this very nice platform that can be teleoperated. Here in the background, you see the operator with the visor and the hand exoskeleton, and this allows the operator to be merged into the environment of the robot, then operate for example, this plastic protection to get out the fire hose or open a door, or use this manipulation capabilities to retrieve objects, for example, in a collapsed house after an earthquake, where people can't go in again to get their precious objects. The other example I want to illustrate quickly is agricultural robotics. This is a collaboration with University Católica. They're experts in grapes, in vineyards. So here we want to use our arm on top of the quadruped to tackle the problem of winter pruning. So basically every winter the grape vines need to be cut so that in spring the grapes can grow in a proper way. We're using here machine learning to extract the potential pruning points, so the points of interest, and then apply expert knowledge that has been learned by neural networks to then go and approach and do a cut at the correct location. And the other application we're doing very similarly with the same people. This is also a collaboration with Fei Cheng and Darwin Caldwell inside IIT. Here we're tackling the problem of table grape harvesting. We're using, again, a neural network that can recognize the clusters and then also the stem. And with this simplified gripper that you see on the bottom right, we can actually do a very nice combined cutting of the stem and then gripping it at the same time, so that we can then put the grape into the tray or into wherever they are collected at the moment. So these are two examples that I brought today.
Thanks, Claudio.
All right, applications. So, you know, I think the main drivers that people have said for fielded robotics of dull, dirty, and dangerous for years is still pretty primal for the work that we're doing. And just talking about Spot, there's 400 robots in the field, which to me, who's worked on this project basically since day zero, is pretty amazing, just personally. We've been in a number of environments that were hazardous and not quite inhospitable to people. Nuclear plants, Spot went to Chernobyl, offshore oil fields, construction sites in the mines. You know, if you look at the diagram on the right, you know, construction, oil and gas, public safety, mining, there's a common thread there, which is remote inspection. We announced a couple of days ago, we have a new product called Scout to enable that, which is basically a remote inspection suite for a fleet of robots to you know, go across your site and you know, look around. Furthermore, actually, the things that you know, with the previous panels we talked about, we also announced that we're making the Spot arm available for sale. This is extending the robot more than a virtual sensor platform. Then you get into the issues of like, well, geez, drones are easier than you don't have a mobility problem. That okay, now we can actually interact with the world. You can go and turn a valve. You can go and you know, I don't know, open a door, that sort of thing. Just talking about entertainment a little bit. This is Adam Savage from Tested, working with Spot. You know, he's a rickshaw, carrying him around, just to keep this a little bit more lighthearted. Then this is the SoftBank Hawks actually used Spot along with Pepper to. There weren't many crowds at the baseball games this year, and okay, now actually this is some Japanese pop star who's using the robot to do dancing. So, you know, entertainment advertising actually still is a market here for our machines. This was Adidas actually did an advertisement for, I guess they're selling shoes in this case. And for Earl Williams, I think is the person in the video here. And this is utilizing, you know, some of our dancing activities. It's emotive, it's exciting, people like it. It looks like a real dog. This is actually Universal Studios. They had Spot set up with some steampunk sort of accessories, and then you get things like this. I don't even really know what's going on here, but this came up when I was looking for entertainment applications for our robot. So that's all I have. Actually, no, sorry. Okay, applications looking forward. Yeah, so autonomy and remote operations are key to enhancing robots' capabilities. We really want to be able to install the robot into customer sites, get frequent and high reliable data capture. Mobile manipulation, I think, is going to be hugely important, as I already mentioned. Where are we 10 years from now? Hopefully still doing what we're doing, providing real value to our customers. The robots are going out, they're inspecting things, they're interacting with the world when we get there. We can keep, you know, people safer. And also, we're going to display a large family of payloads. The robot is primarily a thing that's going to carry something around on its back. So you want to have camera systems, you want to have IR imaging, you want to have LiDARs that you can deploy and to provide the data capture that are useful to our customers. And that is all I actually have in that.
Yeah, so the applications at Ghost we're looking at, today, I would characterize them all as sort of being under the umbrella of mobile sensing, where, I just picked a few applications that we're working on just from our website so that I don't get in trouble. But yeah, so some of them are persistent security. So for instance, yeah, the robot is carrying around sensors trying to, patrol some site, whether it be an industrial site or a defense site. We have applications that we're working on in construction. So here, there are people like Lego robots to be able to work through unstructured terrain, such as you see here with, maybe the weather's bad and there's water and things like that. Or maybe mapping in mining. So this is a collaboration with a company that makes a sensor for this purpose. And of course, the terrain is quite rugged, as you can imagine, in mines. So these are some of the applications that we're looking at today. And thinking ahead about the applications of tomorrow. In the near term, we're thinking about mobile manipulation. It's been mentioned a couple of times, and obviously, if the robot can manipulate its environment, there could be a lot more applications there. We're really looking at more autonomy. So this is one thing that hasn't been talked about yet, but we have rudimentary autonomy now. The robot does kind of things that it's told, patrol a work site, things like that. But we got a flavor of this from the DARPA sub-T challenge that we saw less than a year ago. And yeah, just having unsupervised ability to explore, maybe in a search and rescue scenario and things like that. That's something that we're looking ahead to in the future. And really, going to my crystal ball here, I think in 10 years we'll hopefully be able to start talking about applications where the robot's not kind of hidden away in an industrial site or things like that. But there are lots of very tough challenges to solve there, including how much noise a robot makes, how safe it is to be around, and of course, like very, very mature autonomy. And also, kind of the things that we're missing just from the side of controls, which is most near and dear to me, is just kind of general dynamic stability. I won't show that Goat video again, but yeah, kind of thinking ahead to the robot being in all sorts of terrains and environments. Obviously, controllers need to be more robust and also versatile. So it's the kind of stuff we're thinking about.
Thanks a lot, Arik. I'm happy that you brought up this last image, or the second last image of sub-T challenge. I think it's a good sign for this community to see that by the finals this year, we're going to see probably like robots in all the teams. So that shows like where mobile robotics in this challenging environment has to go in the near future in order to make these things possible. So we have time for 1 or 2 questions. I have to ask one question, which was upvoted most here on Slido. That there was recent videos of ghost robots equipped with guns. Sorry, Avik, I have to ask this. I think this is important, apparently for many people here. So the question there is like in terms of application, if this is an application and to what extent this is an application.
No, I mean, absolutely. So I'm trying to think of what this video might be. We did do a partnership with a company that makes EOD. Devices that are meant to immobilize, explosive devices. So maybe that's what people are referring to. Well, that's certainly not an aggressive or offensive sort of stance. And yeah, we certainly don't want weapons on our robots. And yeah, we definitely don't want to go into that kind of application.
Thanks. Other questions? Front row people, maybe.
I'd like to go.
Oh, sorry.
Oh, okay. Go ahead.
Yeah, okay. So I have one question. So you talked about many applications, and I think the applications like focused on mapping and inspection and small payload manipulation. But the big dog and LS3 were developed for like high payload, you know, carrying and developed for like carrying very heavy load for the soldiers. But I mean, currently the quadrupedal robot is only used for like mapping and, you know, inspection. So can any of the panel talks about like what kind of, you know, improvement we should have for control design and mechanical design to make the robot carry high payload. So yeah.
Well, maybe I can take this. I can make a start. I think it's a really good question, and we haven't had time in round one to talk much about this. Maybe the question about when do you want electric actuation, when do you want hydraulic actuation? And I think when you go up with the payload and the force requirements from the machine, you're probably better off with hydraulics, and you're also in an environment where it's already a bit more dangerous. So the potential safety hazards around the machine are a bit less of an issue, like excavators. Think of a demolition machine that can go into nuclear environments and start to dismantle the machine with legs, for example. And I think that's where I see the heavier payload machines come out. But these machines are more expensive, and I think we're seeing now the market is starting with the less expensive machines first in applications where maybe the payload is less, and I think it's great to open up the market, and this will help pave the way also for the higher payload machines, I'm sure.
Thanks. Peter.
Yes, thanks. You know, for the big acceptance of like a robot, certainly there's the technology and also the business case behind it. But I think what we face often is on the concerns of certification and safety. So my question to the panelists is, how do you think about it to make your robot safe, the certification aspect, because you're really pushing here novel devices that are not out there. So what are your approaches and strategies and thinking behind it, and how these machines are supposed to be designed to be almost intrinsically safe?
Probably one for Avik or Ben.
Yeah, the certification problem is hard. I don't deal with that. we hired somebody who's an expert in this field to manage it for us. But yeah, so safety concerns is obviously something that we care about a lot. You know, our robot, while we, you know, as engineers who work with it, might get a little bit closer than we're supposed to do on a day-to-day basis, we still do recommend that you stay, you know, I think it's 1.5 meters away from the robot. We'd like the robot to be able to understand when it's okay to you know, the robot's energetic, it can be reactive. Those are things that make, you know, close interactions with humans actually a bad idea, because you don't know that it's reacting against it's slipping, or it's reacting because it's hitting somebody. So making the robot understand when it can be energetic and reactive and when it can't, I think is the next big thing to make it so that these can be closer interacting with people in the buildings. So yeah, that level. And the certification thing is a problem, yes, because I think that mobile robots interacting in buildings with people, a lot of certifications are a little bit targeted towards sort of factory robotics, which is a completely different domain. So yes, I think it's an emerging field. I think it's probably going to change. And thankfully, I don't have to deal with a lot of this stuff, and we're going to pay somebody else who's an expert in that field.
Yeah, I'll just add that, yeah, this is also a field we're, you know, learning about. You know, as you saw, I put the going into consumer areas as like a 10-year problem. It's probably quite challenging to figure out all the safety issues with that. And yeah, for now, we're, you know, we just want the robot in the factory or far away from people as much as possible.
Thanks a lot for that, and I really hope that, you know, the companies you're pushing together with us, that will find a good way to address those concerns from the public, that we can really see mass adoptions like robots.
Okay, great. I think this is a very nice transition to the last set of questions. I don't have to share my slides for this. The last set of questions deals a little bit with the shift that we are seeing between things that were like pure research, foundational research happening at universities, and now with all the companies like Boston Dynamics, Ghost Robotics, Unit3, Deep Robotics, Anybotics, like many more that are like showing applications and performance, which is from time to time even beyond what we see in research. And if you look actually back, it was a similar trend what we saw also in autonomous driving. So the question to you guys is a little bit, where do we still see the need for research at universities in the field of quadrupeds, and what is primarily becoming like an engineering problem? And in particular also for the younger PhD students that are joining in, or even master students that are joining in, what are the big open questions that we still have to solve in the next couple of years, predominantly from a research aspect?
I can start. Honestly, quadruped has a slightly different story, because I think that a lot of academic people, like including me, were actually inspired by Boston Dynamics work, and then followed the Boston Dynamics. But regardless of the history, it is true that the trends are all companies take over and making a lot of progress, and academic institute has to think about what unique contribution we can have. Short answer is there's always like a problem that doesn't necessarily need to integrate tens of components and algorithms, like a context modeling, for example, or a context sensor, or some reactive behavior and specific to a certain situation. So it could be a lot more pure research. The integration is some sort of hassle for academic. The academia is always focused on the new or novel contribution, either theoretical or approach. If you spend a lot of time just integrating system, is not very productive for academic people. So that's why I think once the some enabling technology rise up, and then integration is mostly taken care of by the companies. The academic people also get benefit out of it. Like people who cannot build a robot is too much work, buy Boston Dynamics robot or Unity robot, Quadruped Robotics robot, and then they just buy a camera sensor from Intel, and then the NVIDIA computer, and then they can do their own research. So I think there's still there kind of sort of complementary aspect of it. But when it comes to really making like progress, like integrating vision and integrating arms, it's academics. I think is in order for academics to do all of those, I think is just too much, in my opinion. So like a leading, sort of like a capable, showing some capability and then showing this entire control framework. I think academia need to position our, itself slightly more strategically, like there's some, as I said, something specific like control the context dynamics or context sensors. And I guess a lot of academic people are focusing on balance controller. I guess like balance control by itself, I honestly feels is getting very mature. So all these research questions arise on a lot more high level, like abstract level, like what is the right thing to do it's no longer relying on this model based some control algorithm. Is actually more compounded question, and like a planning, high level planning, and so on. So I think still there are plenty of things to do as an academic person, but we gotta be careful not burning ourselves, like integrating a bunch of tools and spending hours in engineering problems. Yeah, that's my short bits.
Okay. Here are my thoughts about the open questions for the future. I put together a short list of open challenges that came to my mind, and one of them is machine reliability, to get the machines to a point where they can be as reliable as a car. Maybe implemented with component redundancy, how we've seen a little bit in Segway, where some of the components are actually redundant in there for safety. But also whenever we bring the machine into an extremer condition where there's, for example, radioactivity or acidity or other matters, we've already seen briefly, I think Ben mentioned it, that a spot has also gone into Chernobyl. Back in 2007, we made an animation about the early concept of IQ Real, and we had in mind also this nuclear use case in which we would bring legacy systems to go in and do certain tasks. There's lots of buildings all over the world that were used for nuclear research back in the 50s and 60s. And these buildings are crumbling down now and need maintenance, need inspection. So in this animation, we were stepping here over pipes and showing how the robot can navigate over rubble, and just to stress the point in which legged systems are important. So, and I believe that these are some of the tasks that the industry can do very well. On the other hand, when we look at academia, we're very good in algorithms development, both for locomotion and manipulation. The question where we have a good mix between model-based and data-driven methods, which we've discussed extensively today, but also novel robot design. Maybe the quadruped robots don't always need to look like that, and there's other advantages. Hydraulic actuation efficiency, if we want to do a hydraulic robot, but then also new sensors are developed, and they might open up new doors, and we have new data types that we can integrate to improve our controllers. Also skin on the legs, for example, to use them for more tactile. But then also advanced teleoperation that we've seen with AR, VR is, in my opinion, things that academia can still push a lot and help. In terms of algorithms development, we haven't seen much so far with collaborative manipulation. So where 2 robots, 3 robots work together with manipulation to do a task which one alone would not be able to do. This is certainly a nice topic. But also whole body contact optimization, in which we have other points in the body that we use for contact, not just the feet and the end effector. I'm thinking of elbows and shoulders and bellies, or whatever other part is not normally in contact. Local manipulation plus, we've heard before. I think there's still a lot of room in using the manipulation on the quadrupeds. But also just pure research in locomotion still, where we're just looking at more challenging environments. And we've recently worked on this a balancing act here, where the robot is in simulation of walking over a 6 centimeter narrow bridge. And we've then also tried the same algorithm of balancing on 2 legs that could help in the future to push robots into even more challenging environments. Another open question is actually whether we can use legged systems also for space. We haven't really heard much about this so far, but we have recently won a contract with the European Space Agency to explore exactly that. So we're applying our locomotion controllers on hexapod and quadruped robots to explore if this could be a way to get into locations where traditional rovers cannot go, like craters or caves. We're hiring robotic software engineers related to this project. And because this is my last slide, I thought I have to thank my team at this point and point anybody that is interested in knowing more to our website or socials.
Thanks, Claudio. I only have one slide here. I think the question was more or less, has industry figured it out? And the answer is certainly not. I think a strong academic research program is vital to our industry. We read papers all the time. We try to stay on top of what are the latest things, including things like learning. Just as Boston Dynamics support towards academic efforts. We have special academic pricing on the Explorer model spot. The ARM API, it does expose the low-level interface for manipulation research. We don't, at the moment, provide the low-level API to the for the legs. I think our perspective here is that if we're going to provide the mobility platform to you, we're going to provide the right API that you can interface with it, but probably for mobility research, that it's not the right platform for you right at the moment, unless you're going to use it as a mobility tool. Just talk about the academic pipeline. Many Boston Dynamics engineers were in research labs previously. Recent hires from MIT, the MIT Biomimetics Lab, UTH Zurich, Romola, UCLA, and so forth. And we need to expand, the field. Boston Dynamics itself was a spinoff from the Leg Lab 20 years ago, and I guess Quadruped Robotics also a spinoff from UPenn. So, I think that just speaking more broadly, that the fact that we can talk about a quadruped robotics industry is fantastic, and we need to grow the pie. You know, we need to make the pie bigger. So the fact that there are other companies doing the same thing proves that this is not just, you know, I wanted to work on quadruped robotics because I thought the idea of, you know, biomimetic robotics was interesting, not because I thought there was a huge need for it. This was years ago, watching videos from Mark Rayberg at the Leg Lab. So the fact that you can say that there's an industry here is great, and we need to keep it going. And yeah, that's all I have.
Yeah, so I actually I have a lot of opinions on this because I've been very involved with academia. I got my PhD. I was actually doing a postdoc for the last 2 years. Now I'm at Ghost full time. So there are the two sides: the companies and the educational institutions. So if you think about why we need the companies, in order to help academia. So firstly, there's the motivation of real world problems. We just talked about applications. And maybe, we're also very happy that Boston Dynamics is, in the space, and we're learning about new applications every day. And eventually, this all filters down to people who are interested in the research, in giving new problems to work on. The second is the platforms themselves. I think Sangwei mentioned this, but and I found out myself when I was a PhD student. It takes a lot of time to build a robot like this. And obviously a PhD student's time is limited, their resources are limited. So the ability to have platforms, to not have to reinvent the wheel is obviously a huge boon. Money, so companies obviously, with their applications, hopefully will be able to make some money and furnish these platforms instead of having to be paid from NSF funds, which are already quite limited. And of course, the part that never goes into the research papers, which is just making the system that last 10% more robust, just to make sure it doesn't fail in these edge cases. Obviously, the companies can't ignore these things, and I truly believe that these situations also present interesting research problems that should go back to academia as well. But on the other hand, why do we need universities? Well, so firstly, to train people. It's been mentioned about how hiring for these companies often comes from, almost always comes from PhD programs, and we've had a great pipeline straight from Dan Kodacek's lab at Penn into Ghost for the moment, and we're obviously always looking for students coming out of labs who are interested in this kind of stuff and have some of the training necessary. The other reason I think we really need the universities is that, at least at a small company like Ghost, at a startup company, it's pretty hard to justify spending a lot of time on problems that won't have any commercial return for maybe years. So Boston Dynamics is able to have a program where they can do this, and obviously universities are really the place where this happens. So we really need universities to be able to keep these kind of longer term problems to keep working on them. And also intellectual freedom. So, we have talked about today about a lot of kind of converging approaches that seem to be working well today. But it's also important to be able to put some time into things that maybe don't, immediately give you something that's going to make money, but go off in a different direction to maybe give us a lot more return in the future. So I strongly believe that that's quite important. So what does this mean for an individual? Maybe a student who's in a PhD lab at the moment, and they're thinking about if they want to either be a professor or be in a company. This was me just a few years ago. So they're kind of in the middle, right? And I think it's worth thinking about what their future looks like. So as I mentioned, I really think it's beneficial to draw on both. But the things that are quite unclear are, and I think this was a question in the chat as well, what are the incentive structures around IP? So companies are incentivized to kind of keep things secret, and the academic is incentivized to do basically the opposite. So I don't know what the answer is here. So maybe there's some kind of way to incentivize companies to publish more. It's obviously the companies have a lot of constraints here. So yeah, this is something that I think we need to work on to have a more kind of beneficial relationship. And just to quickly leave my opinions on big open questions, I think I mentioned some of this before, but hierarchical control structures that can combine all of the different things that we've talked about today. I think that's a really interesting direction of research, and is going to be very fruitful in the future, I believe. Generalizability of RL, and I think this is something that we're really looking forward to be able to use these tools effectively. And yeah, I guess that's where my presentation ends. Thank you.
Thanks a lot. And with this, we're at the end of the official part, and now it's time to ask a couple of more questions. So maybe front row can go first, and I have a couple more from Slido. Anybody who wants to jump in for this? Yeah.
Yeah, I'll start us off. I'm going to have a long rambling question, but when you look at a sky high level right now at the quadrupeds that are out there, it looks like Boston Dynamics had a big dog and a little dog, and we've kind of morphed toward a medium-sized dog, and a lot of the designs look very similar. A lot of the motivation for these robots is the goat videos that we always see, the cheetah videos that we always see. The goat is able to deal with keeping footholds on complex surfaces. The cheetah has maneuverability, maybe something like an ape that is multi-limbed. I worked with a robot that claimed to be simian-like, that was not simian-like at all. We're going to have applications in low G, which is going to change the morphology. Maybe the solution is to have a centaur with arms. So the design space is actually much larger than what's been converged on right now, which I think, if people are looking for new ideas, there are lots of ideas out there. What are people's thoughts about the trade-offs in size and morphology and what the future holds and whether to encourage people to do crazy robot designs or not?
I can jump in on the size thing a little bit, just because yes, our robots have run the gamut. So when we went from Spot Classic, which was the 70 kilogram robot, that's because we wanted to go indoors. We wanted to operate in human-sized environments. So that actually does limit the size of the robot that you can have. And okay, now once you're in a human-sized environment, if you really justify the complexity and the cost of a legged robot over a wheeled robot, well, then you really need to be able to go up and down stairs. So that actually provides a low end scale. So little dog probably can't get upstairs. You could probably ramp it up a little bit. So there is sort of because we're operating in human environments built for humans, there is sort of you need to build a quadruped robot that fits on human-sized things. You need to be able to fit in the hallways. You need to be able to turn around on stairs landings. Stairs landings are actually really hard. The robots are long. If the quadrupeds are longer than a biped. So in regards to the morphology question, yeah, there's a huge space there. When you think about low G environments, you really want a thing that looks like Spot, or you want something that looks like something else. But even across the robots that we looked at today, you see some very subtle morphology differences. Just even about which ways do the knees face. Our cheetah robot, Wildcat, everyone thought it ran backwards, and then Spot, we changed the knees around, and then Big Dog had this forward to freedom leg, and then you can see like Animal has the knees pointing together. So there's a lot of difference. There's actually a big concern. We study this a lot for stair climbing, because that was principal importance. So, but it's an interesting problem, and I think there's a whole big space there that people really should be researching.
So maybe something else to answer to that is also right now we achieved a level where we can also think about a lot of designs that are more driven from an application point of view. So far, it was a lot driven by curiosity, the stair climbing problem, and also about availability of technology. Now, having a certain level achieved, I think there's a lot of new designs coming in, which are much more driven than also by what the system is actually supposed to be doing in the real world application. And so far, people have only to limited extent thought about that.
Yeah, I want to add something to this. If you look back, all these automation tools, like really broadly speaking, like if you think about machine that do all these chores in our house, would we have one machine do everything, or would we still have a laundry machine, dishwasher, vacuum cleaner, and so on? So Marco talked about the application specific. You have to really think about in the future, are we going to have a one robot morphology can do many, many things? Or are we going to have a specialized machine that can do only one thing very well, but much, much simpler? So that's something we need to really think about as a roboticist. And academia, we're just purely research, but when it comes to application, what really worked in the history, and you have to really plan properly well. How much cost would you pay for the versatility, or would you split the functionality and then make each individual robot simpler? That will probably answer the morphology question.
So this connects also to the question that we had on Slido, which was why are quadrupeds still expensive? And did we hit somewhere a limit now, and or to what level will we be able to like reduce the price in the near future?
I can talk about this a little bit. So yeah, we've obviously put a lot of time into trying to not use crazy components that shouldn't cost very much. So one thing is that design for manufacturing takes a huge investment. So Go certainly as a company isn't quite ready for that yet. We're still kind of iterating on the design. So that's one reason things cost probably like 2 to 3 times as much as they should. The other thing is a large component of our cost has started to become sensors. So that's somewhere we don't have the expertise, and we'll have to kind of wait on the industry a little bit. But we're always trying to the fundamentals of design, as well as nitty-gritty stuff like supply chain and sourcing components. We're always trying to make the cost lower, but yeah, we're not able to really get the economies of scale yet.
Just to touch on the cost a little bit, it was not that long ago that a Boston Dynamics robot would be, multiple millions of dollars just in materials costs, and not even including engineering time. So I think if you look at the, cost per robot over time, that it's headed in the right direction. And the fact that you can go, and I don't know, just talking about Cheetah Mini, that if you look around, you can go to AliExpress and purchase one for, I don't know that it will ever show up, but you can purchase one for $12,000. That seems like a pretty good price for a fully actuated robot with balance. So I think as time goes on, those price per robot will continue to go down in the manufacturing thing. We spend a bunch of time on that.
Okay, any other question here? Then maybe I have a last one from Slido to close this. And this question is, why are we not just working as much on state estimation and perception than we work on control and planning? I think this connects very much to where the future of electrobotics goes. So maybe who wants to pick this question?
I can answer quickly. Is probably not a great answer. We spend a lot of time on state estimation. It's just this is a typical engineering problem. Very difficult, but there's not much to publish. So it's a pretty badly ill-posed problem for academia, because typical good papers are very new mathematics and they're very clean environment, and you propose why is it effective. In the regular robot, state estimation problem is probably one of the worst state estimation problem, even worse than drones, because there's shocks and shaking and so on. Boston Dynamics figure it out, but when it comes to publication, that's probably why it looked like we're not working on it, but it's actually we're spending a lot of time on it.
And maybe to add, I think on the perception side, we're going to see something which was similar to what happened in autonomous driving. Autonomous driving converged to a perception problem. And I think a lot that has to deal with autonomy for our machines is even worse, because we have an even more complex environments. In a couple of years or decades from today, we're going to talk about all kinds of different perception problems in this context. But first, in order to achieve this, you have to have some machines that can actually do what they're supposed to be doing if you tell them what to do. So I think with this, we have to close here. Let me very briefly go back to this. So it's, first of all, it's unfortunate that we couldn't do this in person, the whole thing. I hope we have soon again, like conferences where people can come and touch and work with this robot together. It's a lot of excitement around this. I would like to thank all the people that were involved in that, the whole panel, the whole front row, for a very stimulating and exciting discussion. And I would like to close with an announcement of the next colloquium of IFRR, which happens in 2 weeks from today, February 18th, on human-robot interaction. With this, we are at the end. I thank you all for attending, and I wish you good night, good day, good whatever. Thanks, everyone. Bye-bye.
Thanks a lot to all the panelists.